morning. Thank you all for being here on this last day of DevOps 2024. And thanks for choosing this talk. The title is Continuations, the Magic Behind Virtual Threads. Virtual Threads, as we know, is an important feature of Project Loom, and it is also released as a final feature in Java 21. It also promises to bring high scalability. But the real hero of the story is continuations. Continuations is actually the magic that enables virtual thread to provide high scalability. And that is exactly what we're going to explore in this talk. But before we begin, I want to do a very quick poll in this room. I just want to quickly check if anybody has an application that uses Java 21 or higher, even one application. Well, that's, let's say, about 30% of the room. I would expect to be a little bit more, but still, that's pretty good. Now, all the people who raise their hands, they have the possibility of using virtual threads. So I just want to check how many of you are actually using virtual threads in your applications. Okay, let's say 10% of the room. It could be more. Well, thanks for raising your hands. Now, in this talk, what we're going to do is, actually, the talk is divided in 3 parts. In part 1, we will get a little introduction to virtual threads. In part 2, we will explore what continuations are. And in part 3, we'll actually use this knowledge of continuations to create our own version of a simple virtual thread. So let's get started. But first, a very quick intro about me. My name is Balkrishna Rawool, and I work for ING Bank. Okay, start with the part 1, which is introduction to virtual threads. So what we see here in this picture is actually an instance of JVM, which is running on some operating system. And the JVM has a bunch of virtual threads, also a few platform threads, and OS has some OS threads. Now, let's start with platform threads. So platform threads are actually a thin wrapper over OS threads. What that means is when JVM wants to create a new platform thread, it actually requests operating system to create a new OS thread, and only when that thread can be created, it creates an instance of a platform thread. And therefore, these platform threads map to this operating system threads with a one-to-one mapping, meaning an instance of platform thread has one and only one OS thread connected to it. Also, creating a platform thread is a resource-intensive task. So you don't want to do that too often. When you have a platform thread and when you don't need it, you don't want to throw it away. So you put it in a pool so that the next time you need it, you can get it from the pool. Virtual threads, on the other hand, are lightweight user threads. Lightweight meaning they require significantly less memory, and therefore we can create them in abundance. We can create thousands or even millions of virtual threads, and that makes them highly scalable. There's actually one more thing that makes them highly scalable, and we will see that on the next slide. But another thing about virtual threads is that they don't require pooling, because creating a virtual thread is a cheap operation. When you don't need it, you can just throw it away, and next time when you need it, you can create a new one. In fact, pooling virtual threads is an anti-pattern. You don't want to do that. Now, if you look at this picture, we see some of the virtual threads are connected to platform threads. Why is that? Because a virtual thread on its own cannot execute anything. It requires a platform thread to execute something. But what about these other threads which are not connected to the platform threads? When do they get the platform thread? Well, for that, we have a virtual thread scheduler. This is a newly introduced scheduler along with virtual threads. And what it does is it actually mounts a virtual thread onto a platform thread when a virtual thread requires platform thread, and it unmounts the virtual thread when it does not require platform thread. Now, what would be the scenarios where a virtual thread would not require platform thread? It is when a virtual thread is waiting for something. For example, let's say it is waiting for a network resource to be available or a database to return something. Now, in these cases, virtual thread does not require any processing. It's not doing any processing, so it does not require platform thread. It does not require CPU, so it gets unmounted from the platform thread. And a typical I/O-bound application, threads spend a lot of time waiting. And all of that waiting can be avoided if we use virtual threads. So if you use virtual threads, all of that waiting can be avoided, and your CPUs are not blocked. So therefore, CPUs are highly efficiently utilized. And that's what makes virtual threads highly scalable. Also, in this entire endeavor of mounting and unmounting, the platform threads are carrying virtual threads. Therefore, they are also known as carrier threads. Well, that's a lot of theory. So what we're going to do now is we're going to create some threads. So let me head over to IntelliJ. And I hope the font is big enough. I've actually increased it quite a lot. So in the back, can you see? Can you read it? Yes? Okay, I get a yes, so just going to continue. Okay, let me first create a platform thread. With Project Loom, we actually have a new API to create a platform thread, and we can do thread.offPlatform. And this gives us a platform thread builder, onto which then we can call start and pass a runnable to it. In this case, I'm just going to print the current thread. So if I run this, I will see that it actually creates a platform thread. There we go. And you can imagine a similar API to create a virtual thread. Just change this to of virtual, and this will create a new virtual thread. And there are a couple of things to notice about the virtual thread, at least a two-string representation of the virtual thread. One is that this part. So this is actually the ID of the virtual thread, and it is unique for each virtual thread. Also, this part, things after add. So this is actually a platform thread onto which this virtual thread was mounted when it executed this statement. So you get some information about the carrier thread as well. And there's also a shorthand method, so you could simply do start virtual thread, and this will create a new virtual thread. Also, there is another way to create virtual threads, and that is to use an executor service. So I'm just going to do that. Variable executor. This will be executors dot new virtual thread per task executor. So what this does, it actually gives me an executor service, which gives new virtual threads. So that it is not backed by a thread pool, and it gives me a new virtual thread every time I request it. And the way to do that is call submit on it and submit a task to it. And again, I'm just going to print the current thread. So if I do this, it will give me a new virtual thread. There we go. I can actually create a bunch of these. I'm again, because I'm using try with resources, this ensures that all these virtual threads are finished before I exit this try block. So now if I run this, I should see a bunch of virtual threads here. And if you look at these IDs, they are all unique. That means all these virtual threads are different. But if you look here, we have a bunch of virtual threads which are using the same carrier thread. So what's happening here is that this virtual thread was mounted onto this carrier thread, and then when it was done, a new virtual thread got mounted onto the same carrier thread. So how is this mounting and unmounting happening? And because this mounting and unmounting is driving the high scalability, what is it that is actually giving that high scalability to these virtual threads? And the answer to those questions is continuations. So that's the end of part one about virtual threads. Now we're going to look at continuations, starting with what is a continuation. So a continuation can be viewed as a representation of the current state of the program. Now your program could be as simple as sequence of instructions, or it could be a bit more sophisticated with nested method calls or nested loops, but you can get a continuation at any point in time, and that continuation would be an object that would represent the current state of the program, including these nested method calls, including the iteration of the loop that you were at when you took the continuation. Also, when you take the continuation, your program is paused at that point, and then you get a handle to that continuation object, and then you can pass that object around in your program, and you can decide to resume the program at that point. And then the program continues, and then it continues, takes it to its completion. So you can also imagine the continuation object as the rest of the program or the rest of the continuation. So a continuation can be viewed as a representation of the current state of the program, or it can be viewed as the rest of the computation. Okay, what is the use of that? Well, it's the use that it allows us to pause the execution of the program and then resume it later. Now, we will see that with some examples when we explore the continuations API in Java. But before that, I want to highlight something, and that continuation API in Java is not supposed to be used directly by application developers. For now, it is only used internally and only used to create virtual threads. But then you might ask, why are we studying it? Why are we looking at it? Well, three reasons. One is that knowing continuations would help us to understand or help us to get insights into the behavior of virtual threads. Secondly, it will tell us how mounting and unmounting is happening. Basically, what is it that is driving this high scalability behavior of virtual threads? And thirdly, because it is fun. So, okay, let's go ahead and see some examples in continuations in Java. For that, I'm going to open another file. Okay, what I want to do is create a new instance of continuation. And let's say I get that from this method called getContinuation. And this method returns a continuation. Okay, I just said that continuation is only used internally, but how am I able to use it here in my application? Well, that is because I have asked the compiler to expose everything in java.base module. Again, if you see this, it is an indication that your code is not supposed to reach production. So don't do this for your code that is going to production. But we are doing it now because we want to just explore continuations. So for now, it is fine. So let me create a continuation object. I can do that by just using new continuation. And a continuation requires a continuation scope and runnable. So let me create a continuation scope first. So continuation scope, you can think of it for the purpose of this talk as the namespace for your continuation. And here I need to pass a string. It could be anything. It could even be empty, but I'm just going to pass demo here. And then I passed runnable. And in this runnable, let's say I'm printing few things. So I'm printing A, and then B and C. And then I simply return the continuation. And then when I have a handle on the continuation, what can I do with it? I can run it. So let me run this and see what happens. Well, I see A, B, C printed. So basically, running the continuation has just run the runnable. There's nothing fancy going on here. But because the runnable is wrapped in a continuation, we get certain power. And the power is to pause the execution of this runnable. And the way to do that is to call continuation.yield, then pass scope to it. And I want to do that at two places. So if I do this now and run this, what I see is only A is being printed. So what happened here is that the runnable got executed. It only executed this statement, and then it encounters this yield call. So it pauses the execution of this runnable. And it not only pauses the execution there, but it also transfers the control all the way back to here immediately after this continuation.run call.
So is this running on the same main thread or on a different native thread, on a virtual thread? Where the continuation is running?
On the same platform thread. So we'll
On the main thread?
yeah, the thread that started it. Yeah,
okay.
yeah. Okay. So the question was where it is running, and it is running on the same thread that it started in. And then actually it transfers the control here, so I can do something here. I can do something. And if I run this, what I see is it basically prints A, transfers the control, and it allows me to do something. But the continuation is paused here. How do I resume it? Well, I can just call continuation.run once again, and it will then resume the continuation from there. And it prints B. So what happened when I called this run? It actually took me back to the point where it was paused. That was this point. And then it started executing the runnable from there. And then it does that, and then it encounters another yield point. So it went from the last yield point to the next yield point, and then paused there. Okay, how do I resume from there? Well, I run once again. So if I do this now, it will resume the continuation, take it to its completion. What if I do it once again? Well, let's see what happens. We get an exception. It says that the continuation is terminated. So once the, let's say, runnable is finished, your continuation is terminated. But there is an API to find out if the continuation is terminated or not. There is a method called isDone. We will discuss that later. But for now, let me not do this and only execute continuation until it is finished. Okay, now before I move on, I just want to highlight a couple of things. One is that this continuation.yield call, it does not have to happen from the body of this runnable. So you can have nested method calls, and you can do yield there. And then in that case, the execution would pause at that point, and it would transfer the control all the way back to the continuation.run, in fact, immediately after it. And the second thing is that this continuation.run, again, does not have to happen from the body of this method. You get a handle to the continuation, and then you pass this object around in your program, and you can decide to resume at any point in time. Okay, so we have seen now how you can use continuation to pause and resume execution of your runnable. And also this control transfer, it looks pretty abrupt. So how is this happening? Well, this is happening mainly with the manipulation of call stack. So let's explore that with another example. We have seen all that, so continuation Java. So let's see what happens when continuation.yield is called. And for that, I'm going to use an example where you have a simple main method which calls a method A. And this method A creates a new continuation object, and it does continuation.run. And in the runnable, we're just calling another method B. And this method B calls C calls C calls continuation.yield. So this is where the continuation should pause, right? And it should transfer the control all the way back to method A, because that's the method that did continuation.run. Okay, so how is this achieved? For that, we have to look at stack memory. And in this case, the stack is getting filled from bottom to top. And also heap memory. So when we call main, we have a new frame created on the stack for main. And that calls method A. A actually creates a continuation object on the heap. And then it calls continuation.run, which calls method B, which calls C, and then that calls continuation.yield. Now, this is where the control should get transferred. So how is that achieved? Well, all the stack frames from continuation.yield until B, they are moved to heap. In fact, they are moved to the continuation object, and they are saved there. And then on the stack, the continuation.run method that returns to method A. And effectively, you have the control transferred to method A immediately after the continuation.run call. So this is how the control transfer is achieved in continuation.yield. Now let's look at what happens in continuation.run. So once you have the object, you have paused it, and now you want to resume it. How is that happening? Again, we have the same example, but in this case, we also call a method D. We have this A, B, and C. And what happens in method D is you do continuation.run. So you basically resume the continuation object, and it's the same object that was created in A. So let's take a look at stack memory and heap memory. But in this case, we have our continuation object with these frames saved in it. So what happens when we call main? It calls method D, which calls continuation.run. And now here, the control should get transferred back to the point where the continuation was paused. So how does that happen? Well, all the stack frames which were saved in the continuation object, they are moved to stack. And then the top stack frame, which is continuation.yield, that returns to method C. So you have this effectively the control getting transferred to the last yield point. And then it resumes from there. So that's how this control transfer is achieved. So this wacky control transfer, what is it good for? Well, many things, including these 4 things. So you can use this continuation to create virtual threads or green threads, obviously. But you can also use it to write your own version of coroutines or exception handlings, and also generators. Now, in this talk, we are actually going to explore 2 of these uses. Firstly, generators, and then virtual threads. So let's take a look at generators. First, what is a generator? So a generator is actually a data structure that allows us to write a function that yields values. Normally, when you have a function, you get one value as a return. But with generators, you can get multiple values. You can retrieve multiple values. And not all of them at once. So these values are lazily retrieved. Also, they can be iterated by using a loop. For example, here you have a generator which is yielding A, B, and C. And then we have a consumer which is looping over them by using a while loop. Now, what is the use of such a generator? So let's say you are generating values after some complex calculation or resource-intensive tasks. You don't want to do all of that upfront, right? You only want to do that when it is needed. So that's when you would use generator. Implementing generator in Java is not that difficult. You can use streams because streams deal with multiple values and they are lazily evaluated. So it's pretty easy to implement generators using streams or even iterators or a collection of suppliers. But what we are going to do is we're going to implement generator, not using any of these things, but only using continuations. So let's see how that can be done. Now let me head over to IntelliJ. Hope you're not seeing that. Now you're seeing it. Okay, so generator. What we want to be able to do is create a new generator like this, generator. So let's create this class, public static class generator. And we want our generator to generate some values of a certain type, and let's say they are of type T. And in our case, we want strings to be generated, because if you look here, these ABC are strings, so we want to use a generator of string. And we want to use continuation, so let's add a continuation here. And continuation requires continuation scope, so let's add a scope here. And then create a write the constructor, which will basically initialize these things. So scope would be new continuation scope. Let's say generator here. And then continuation, which would be new continuation with the scope. And then we need some runnable. So let's say we have an empty runnable right now, which doesn't do anything, and then we do continuation.run. Okay, now we want our generator to yield these values, A, B, C. Let's say we have an argument to the constructor, which is a lambda, which allows us to then write that logic to yield A, B, and C. But that's not how the yield keyword in Java works. So we cannot have our implementation exactly same as this pseudocode, but let's try to get it as close to this as possible. Let's say we have a method called yield, which allows us to pass some strings to it, and that this method is available to us on an object called source. Now hang on a minute, and this will make some sense. So we have this source object onto which we can call yield, and we get this source object as an input to the lambda. Now let's define a the source type here, public class source, and let's create a private member here of type source, and let's initialize the source here. And then the input to this constructor becomes a consumer of source. So this would be a consumer of source called consumer, and then in the runnable we just do consumer dot accept and pass the source object to it. So basically we are able to then execute this lambda. Now the only thing that is remaining for us to do is write this yield method, and then our code would compile. So let's write yield here. And what we want in the generator is, we don't want to evaluate everything, right? We basically want to generate one value and then pause the execution there. And the way to pause it is to use continuation.yield. So we'll do that, continuation.yield. And then we pass scope to it. And also we don't want to lose this value that is getting passed to this yield. So let's store it in a private member called value, and then value bt. Okay, so this way we are able to define our generator, which is more or less similar to what we had in mind. But we also want to be able to use it in a loop. How can we do that? So let's say there are a couple of methods on the generator that allows us to use it in a loop. For example, it has a method called hasNext. And let's say it also has a method called generator.next. So let's define these two methods so that we can use it in a loop. HasNext is not that difficult because a continuation has values, the generator has values as long as the continuation can continue. So we can simply return continuation.isDone. In fact, negation of it, because generator has values as long as the continuation is not done. Also, this method next is not that difficult. We can simply return the value that was stored in the source object. So we can do source.getValue, and let's define this getValue method here. Let's make it private. Okay, and then we get the source value, which we can return. And actually, I want to continue the continuation here, but we can't do anything after return. So let's put this in a temporary variable and then return it here. So this way we have our generator defined and also used. So let's run this and see what happens. So when I run this, it actually prints ABC. So basically, generator is generating these values, which actually after evaluating every value, the continuation is getting paused. And the control gets transferred here in the loop. So I can actually do something here. And if I do that, it will basically do this every time a value is generated, like so. And also, we can, in the in the loop. We can break the loop or terminate the loop at any point in time. That way, the entire generator is not executed, but only the part that is needed for us. Again, I will share the link to this source code so you can take a look later. But I actually wanted to show this generator example with continuations because I wanted to highlight the fact that continuations are a general purpose utility. So it is not only used for virtual threads, but it could be also used elsewhere. But we are here for virtual threads. So let's move on to the final part of this talk, which is basically implementing virtual thread using continuations. Okay, so our simple version of virtual thread, it needs to have certain characteristics in order for us to call it a virtual thread. Now, we call them the goals of our implementation. So what are the goals? A virtual thread instance should not use CPU or should not use platform thread when it is waiting or when it is blocked. Also, a virtual thread can get mounted on several platform threads during its lifetime, and a platform thread can support several virtual threads during its lifetime. So basically, that many-to-many relationship between virtual threads and platform threads should be evident from our implementation. Now, these look like pretty reasonable expectations from a virtual thread, right? So let's see how we can implement this. We'll start with virtual thread class, of course, and then we'll create a consumer which will use that virtual thread and will create a bunch of virtual threads. Also, these threads will have some blocking calls. And we will create a virtual thread scheduler, which will have a bunch of virtual threads and a bunch of platform threads, and it will schedule these virtual threads onto these platform threads. Okay, this looks like pretty reasonable design for our implementation. So let's go ahead and implement that. Let's head over to IntelliJ, and I'm going to start with virtual thread class itself. So a virtual thread, in its most simple form, is nothing but a continuation. Of course, it requires scheduler to schedule it and execute it, but the thread itself is a continuation. So if you externalize the scheduler part, then the virtual thread itself is nothing but a continuation. So let's add the continuation here. And continuation requires continuation scope. We know the drill, so let's add a continuation scope. And in this case, I want to make it public static final continuation scope called scope, and let's initialize it already here. Let's call it virtual thread. Okay, and then let's create a constructor public virtual thread, and then initialize the continuation here. It would be new continuation with the scope, and it requires runnable. Let's say we get that runnable as an input to this constructor. So we have a runnable here, and then we can simply pass that runnable to this continuation. Now, we also want our virtual thread to run, so let's add a method public void run. And what run does is it basically executes the continuation. Also, it prints something. It says that virtual thread is running on, and then it prints which platform thread it is running on, and that's it. So we have our virtual thread ready, and this would be let's say this would be it. This would work, but I want to add one more feature to this, which is basically the identification of the virtual thread, which would come in handy when we use it. So let me add a private integer ID here. And in order to set the IDs, let me add a private static final atomic integer called counter, starting with a value of 1. And let's set the ID here, counter.get and increment. And then let's also print the ID here so that we know which virtual thread is running on which platform thread. Okay, so we have our virtual thread ready. We can now go ahead and implement a consumer which is using the virtual thread. So that would be a class demo, and demo has a main method. And let's create a bunch of virtual threads. So let's say VT1, which is a new virtual thread. And in this case, let's say we want to print few things. So I want to print 1.1, 1.2, 1.3, and 1.4. You can think of these as instructions that are being executed by this virtual thread. And I want to create one more virtual thread called VT2. It does exactly the same thing. The only difference is the instructions that it executes, they all start with 2. Okay, so we have our virtual threads. Now, in order to run this, we need our scheduler, right? So let's write the virtual thread scheduler. Virtual thread scheduler. And if you look at the picture of the design that we have, the scheduler has a bunch of virtual threads. And also it has few platform threads. And it schedules these virtual threads onto these platform threads in a first in, first out manner. Now, in order for us to achieve that, it would be handy to put these virtual threads in a queue. So let's say we have a private queue of these virtual threads called queue. And this would be a concurrent linked queue. And then we have a bunch of platform threads. For that, we're going to use executor service. So we'll use an executor service called executor, which will be executors.new fixed thread pool of, let's say, 3 threads. And then we want to be able to start the scheduler. So let's add a method, public void start. And what start does is it actually runs forever. It runs forever and it checks if there is something in the queue. And if there is, it picks that thing up. And then it schedules it onto the executor. So basically, the scheduler is just looking in the queue, and whenever it finds something, it picks it up and then schedules it onto the executor, on the platform threads. And we also need a mechanism to add certain threads to the queue. So let's say we have a method called public void schedule, which takes a virtual thread, and it allows us to add this virtual thread to the queue. So it basically just does queue.add, and then adds the virtual thread. That's it. Okay, so we have our scheduler ready. Now let's use the scheduler in our demo class. For that, I'm going to create a public static final virtual thread scheduler called scheduler. And this will be a new scheduler. And again, let it run in a new thread of its own. So let's say we have a thread which basically does scheduler start and then start the thread. Okay, and now we can add these virtual threads to our scheduler. So we can do scheduler.schedule VT1 and VT2. Okay, so now we will be able to run our program and see what happens. So here we have 2 virtual threads. And if you look at the scheduler, sorry for the noise. If you look at the scheduler, we have 3 platform threads. So when we run this, each of these virtual threads will be able to take one platform thread and then run in their own threads. So let's see how that works. So what we see is that virtual thread 1 is running on platform thread 1. And then virtual thread 2 is running on platform thread 2. And then they run in their own threads parallelly. If I want to execute them sequentially, what can I do is I can actually just change this number of platform threads to 1. And then if I run this again, what I will see is that virtual thread 1 runs on platform thread 1. It runs until its completion. And then virtual thread 2 runs on the same platform thread because there is only one platform thread. And then it runs to its completion. So let me change this back to 3. And then what I want to be able to do now is to introduce the blocking call in the virtual thread. So when the OpenJDK team introduced virtual threads, they also made JDK aware of these virtual threads. So what they did was they changed all the places where there were blocking calls happening. They made those places aware of the virtual thread. Now, we don't have enough time to change the entire JDK with our version of virtual thread. But what we can do is we can simulate this blocking call. Right? So we're going to do that. But before that, I actually want to add one more feature, and that is thread.currentThread. Because when I do thread.currentThread, this gives me handle to the currently executing platform thread. And I want something which gives me access to the currently executing virtual thread. And for that, I'm going to add a public static field here, virtual thread called current virtual thread. And now I have a question. So we want this value to give us a currently executing virtual thread, but there would be multiple virtual threads executing at the same time. In fact, each virtual thread, each platform thread would have its own virtual thread that it is executing. So we want our virtual thread to have different values for different platform threads. So what do we use in that case? What kind of API would we use? Thread locals, exactly. Perfect. So we're actually going to use thread local here. So we can use thread local, and then this would be fine because then we would have this virtual thread pointing to a different virtual thread for each platform thread. But hang on. Project Loom has a better alternative to thread locals. It's called scoped values. So let me use scoped value here. And I can also make this final and then initialize this to scoped value dot new instance. And then all I have to do is set this to the right virtual thread when I run the thread. So I could do scoped value dot where this is set to this virtual thread, run the virtual thread. So basically what this does is whenever you are executing a virtual thread, it sets this scoped value. So scoped value is a better alternative to thread locals. If you are using thread locals, then you can think of using scoped values, but again, they are not a final feature yet, I think. But when it is there, you could use that. So what we are doing is we are using a scoped value and we are setting that to the right virtual thread when the virtual thread is getting executed. Yeah, so I think we have the handle to the currently executing virtual thread. Now we can implement our simulation of a blocking call, and we'll call it waiting operation because indeed it is a waiting operation. And it has a method public static void called perform, and it takes two arguments: name of the thing that you're waiting for and duration, the amount of time in seconds that you're waiting for. And what it does, it just first prints that it is waiting for this thing for these many seconds. And then when our virtual thread is executing waiting operation, we don't want the execution to continue. We basically want to pause the continuation. And the way to do that is continuation.yield. So this will ensure that, our platform threads are not wasted and CPU is not wasted. Let me import this statically. But we also want that our virtual thread, which is paused, to resume at a point when this duration is over, when the waiting is over, right? So let's do something for that. And I'm going to use a timer. Again, there are better APIs to use, but timer is good enough for us. So that's what we'll do. So this will schedule a new timer task, and we want it to execute after duration amount of seconds. And we shouldn't forget to cancel the timer here. And now we want to resume the virtual thread. But which virtual thread, you ask? Well, it is the virtual thread that was executing this perform operation. So we need to get the current virtual thread here. So let's do that. We have a virtual thread here, which would be scheduler.current virtual thread.get. So this gives us access to the currently executing virtual thread at this point, and then we can basically resume it here, which would be demo.scheduler.schedule, and then pass this virtual thread. So this way, we have our blocking operation defined as well. Now let's use it in our virtual thread. So let's go back here, and let's just say that our virtual thread 1 is waiting for, say, network for 2 seconds, and that it is waiting for, and virtual thread 2 is waiting for database for 5 seconds. So now what will happen? Now if we run this, we'll again have 2 virtual threads, and we still have 3 platform threads. So when we run this, both these virtual threads would start parallelly. They would execute these 2 instructions, and they would start waiting at this point, because this is a waiting operation. And then all these platform threads would be available for any other virtual thread to use. So when this virtual thread 1 comes back after it's waiting, it will pick any one of these 3 platform threads. And then it will start executing the rest of the instructions. And after 5 seconds, when virtual thread 2 comes back, it again has all the 3 platform threads available for it, so it can choose any one of the 3 and start executing. Let's see what happens if I run this. So when I run this, I see that virtual thread 1 starts running on platform thread 1 and virtual thread 2 on platform thread 2. They both execute 2 instructions, and then they start waiting. Virtual thread 1 comes back after it's waiting, and then it starts executing on platform thread 3. So totally different platform thread. And then virtual thread 2 comes back and starts executing on platform thread 1. Now let's see what has actually happened here. So if you notice what virtual thread is using, what platform thread, virtual thread 1 was actually being executed on platform thread 1. But after the waiting, it is now executed on platform thread 3. So it has moved from one platform thread to the other platform thread. And if you look at this platform thread itself, it was executing virtual thread 1 at the beginning. But after the waiting, it is now executing virtual thread 2. So it basically executed one virtual thread, and now it is executing some other. So we can see that many-to-many relationship here clearly in this example. So this is how this is how you can implement virtual thread using continuations. But hang on, we have implemented virtual thread, and we say that virtual threads, we can have like large number of these virtual threads, right? So let's try and see if we can have maybe more virtual threads. So let's turn the heat up and let's create, well, if not millions, at least a few thousand of these. Well, so with this loop, we'll have 1,000 of these virtual threads and 1,000 of these virtual threads. So basically, we will have 2,000 virtual threads, which will run on, let's say, 10 platform threads. And the only problem that I can think of is this timer task, because it uses platform thread. But because we have a few thousand, I think it should not be a problem. So let's run this and let's see what happens with our 2,000 virtual threads running on 10 platform threads. But before I run this, I want to show you one more thing, which is I have another demo class. And if I put it to the right side and compare these two, they both look pretty much same. So we again have like 1,000 iterations of this, where on the left-hand side, I have virtual threads, and on the right-hand side, I have runnables. So these two are seemingly simple programs. The only difference is on the left-hand side, I use virtual threads. On the right-hand side, I use runnables. So I have 1,000 of these runnables, 1,000 of these runnables doing exactly the same thing. But the scheduler here does not use virtual threads either. So it only uses platform threads. Again, 10 platform threads. So I have now an example where on the left-hand side, I'm using virtual threads, and on the right-hand side, I'm using platform threads. Now, let's see what happens. If I run this, it runs and runs and runs. Okay, it's pretty boring. So let me put this on the right-hand side and let it run. And while that runs, I want to run the virtual thread implementation. So if I run that now, again, runs and runs and runs. But something has happened. The last entry you see here is a virtual thread with ID 2000. So it's basically the last virtual thread that we started. It has executed last instructions. So basically, all the virtual threads have finished executing all the instructions when you use virtual threads. But on the right-hand side, the platform thread implementation, it is still going on running. And it will go on running. And on my machine, it takes like 15 minutes to finish all of these things. So basically, if you use virtual threads with the same resources, with the same CPU, you can actually get much more things done, provided you have enough amount of waiting in your application. And this is basically the promise of high scalability. So this is how virtual threads achieve high scalability. Okay, so that's the, I think, final thing I had to show. Let me go back to the presentation. Yeah, we did this. So if you want to take a look at all the source code, it is present here onto this link. Well, I actually haven't checked the QR code, but you can check. If it doesn't work, let me know. And also, if you want to reach out to me on Twitter, you can use that handle. And if you did like the talk, then you can also read it nicely in the site. But let's take a quick summary of what we discussed today. So we looked at what virtual threads are. We looked at what continuations are. And then we use that understanding of continuations to create a simple version of virtual thread. And in doing so, in that process, we got really good insights in the behavior of virtual threads. We also saw how mounting and unmounting happens in case of virtual threads. And we got to know how the high scalability promise of virtual threads is implemented. And I hope it was all fun. Thank you. I think we have 5 minutes for questions. Yes, Mario?
Any reason why this thing has not been made? Because it seems generally useful. Is there any valid reason why it is not part of the public API?
The continuation, you mean?
Yes.
Yeah, I think, so again, this is my understanding. So in the continuation, they have done some optimizations which are very specific to virtual threads. And that's why they don't want to make it like general case. I use it in a generator example, but this was something that I found useful and I could do it. But again, they're not very sure that if you use it in other cases than virtual thread, that it could be as useful as. So maybe in future they will make it a public API, but right now it is not. But thank you. The cost of stack frame switching, so basically switching. Yeah, so they are doing quite a lot of optimizations in basically copying and moving these stack frames. Yes, yes, there are optimizations there. So basically, not the entire stack frame is moved like between. Uh-huh. Uh, Right. But the stack it's saved, so I could use. But I can imagine. Yes, you would have a cache miss. But they have done. Yeah, yes, truly. It's just an example to get a feel of continuations. It's not something that you want to do in production. Yeah. True. Other questions? Yeah.
Normal threads, how we determine the count by the amount of cores, etc. that we have. What about the virtual threads?
Yeah, so virtual threads, they use a special group of platform threads called carrier threads. And the number of carrier threads by default is set to the number of cores that you have in your system. So all the virtual threads would use same number of these platform threads, which are basically just an abstraction over your cores. And then you can change that, but maybe you don't wanna. But that's how it works. If that answers your question. Yes.
I expected easy way to specify platform thread to run my virtual thread, but I don't find that easy way to do it. Because if I create executors, there's no any parameter for virtual thread to give the platform threads.
Yeah, but the question is like, do you actually want to have that control of specifying the platform that you want to execute?
Let's assume I have my web server. I would like to use virtual thread, but I don't like to pay all CPU. I would like to limit my.
So yes, there is an argument that you can pass when you start the JVM to specify number of platform threads that you want to use, a number of carrier threads you want to use. So you can reduce.
If I have multiple web server in one JVM, how to do it?
That's a good question. I haven't thought of that, but we can take a look later. Yeah. Hey, Alan.
Yeah, sorry, I only caught the end of your call. Yeah, I can answer that
Oh yeah, sure, Alan.
question. Okay. So what you're asking for is a feature called custom schedulers. It's a feature that has been explored and prototype at the API exposed. There's a lot of issues with it. There's currently 2 more explorations going on around this activity at the moment. So TBD as to whether anything will be exposed. The two things that are being explored at the moment is replace the default scheduler, and the other one is integration with event loops, where people want to be able to use their own set of threads as the carrier threads.
Yes, exactly.
Once you dive into that, there is a 10-page list of things that you actually run into in terms of what has to get exposed. It's much more complicated than it might seem. It's not just exposing an executor. There's a lot more things that the custom scheduler needs to do.
Yeah, thank you, Alan.
Can I just answer? There was a question when I was just walking in about exposing continuations.
Yes, that was from Maria. Yeah. Yeah, I'm not sure if there is a mic available for Alan.
I did not recognize Mario with the new haircut.
But you have a talk at the end of this day, right?
I have a talk whatever the last session is today.
Yes, exactly.
11:30 or 12 o'clock, I'm not sure, somewhere around then. Okay, so the issue with exposing continuations.
We have to go to court.
So it breaks a whole load of invariants. And the only safe way to ever expose continuations would be actually to thread confiners, which
No.
are no good for the sort of examples that we're actually looking at here. Because essentially this is anything that's block structured, locking, all of those things would be completely broken if you were actually able to find and control this.
Right.
If you start doing experiments with things like generators that you have in Python or JavaScript, you'll quickly actually see how these issues will completely break Java constructs.
Right.
So at the moment, there's zero plans to actually expose
As a public API. Yeah. Okay.
just too many things will break.
Right. Okay. Thank you. But we can take this continue this discussion outside.
Yeah, sure.
Thank you.
Great talk.
Thanks. Thank you.